So as we get into 7.1, let's take a look at some examples. So to begin with, we're looking at simplifying or reducing this fraction. So anytime we have the same thing on top and on bottom, that always reduces to 1. No matter what the top and the bottom are, if they're exactly the same, that reduces and makes 1. So notice this numerator and denominator are the same. They're not written in the same order, but remember with addition, they're commutative. So we could write the top x squared plus 2 and the bottom x squared plus 2. We just swap those. They're both still positive. And notice the numerator and denominator are exactly the same. So anything divided by itself makes 1. One of the next things we look at is the domain of a function. And just specifically a rational function here. This chapter is going to be about fractions. So domain means what numbers can we plug in and get an answer. If we look at some examples, if we plug in a 1, that means everywhere we have an x, we're going to put a 1. So on top, 7 times 1 minus 6 over 5. So when we put in a 1, we get an answer. If we put in a 0, everywhere we have an x, on top, 7 times 0 is 0. 0 minus 6 is negative 6, and we get an answer. And it turns out any number we plug in for x, we're going to get an answer. Any number can be multiplied by 7. Anything can have 6 taken away from it, and any number can be divided by 5. 5 might not go into it evenly, but it can always be done. So in this one, our domain is all real numbers. Any number you can think of. Sometimes we use an R that looks like that to represent all real numbers, or we say every number from negative infinity all the way to positive infinity. So that's our domain. So you might say, well, does that mean every function, the domain is all real numbers? Well, not every one of them. Well, what is something that causes us problems? There are certain operations or certain things in math that we can't do. And the main one we're going to look at right now involving a fraction is if we ever have a 0 on bottom. Dividing by 0 is undefined. How do you break something into no pieces? If I've got 5 cookies and I say, okay, I'm going to divide these cookies evenly up into having every group is going to have none in it. Well, if every group has none in it, how many groups of 0 would it take to have to make 5 cookies? Or how many would be in that group if we have no groups but still have 5 cookies? Well, that's not possible. We can't do that. So we can't divide by 0. So any number that would make this fraction have a 0 on bottom is a number that we can't use. So we ask ourselves, what would make the denominator, whatever the denominator is, what would make it equal to 0? So in this case, to get x by itself, we can add x to both sides. So in order for the denominator to be 0, that occurs when x equals 9. Notice, if we put a 9 in place of x, we get 63 on top, but we get 0 on bottom, and we can't have a 0 on bottom. So x is not allowed to be 9. That's not 9. X is not allowed to be 9. And in fact, that's the only number x can't be. Any other number that we plug into our function, we'll get some answer for. It might end up being a fraction for our answer, but we would get some answer. any other number, we would get something other than 0 on bottom. But when x is 9, the denominator is 0, which we can't have. So that means our domain in words is all real numbers except x cannot equal 9. All real numbers except x cannot equal 9. As an interval, we could say everything starting way out to negative infinity, and we get really close to 9. And then on the other side of 9, we go all the way to positive infinity. And when we have two different intervals, we put a u in between. So that's every number except 9. Now, the next problem involves simplifying an expression. So if you watch the videos and you may be aware of, there are certain things we cannot do when we simplify expressions, when we reduce fractions. So another set of instructions might say reduce the fraction or reduce fractions. So it's easy to look and say, well, 5 and 15, those have a common factor of 5. 5 goes into 5 once, 5 goes into 15 3 times, but that doesn't work. Those fractions would no longer be equivalent. You could look at several different examples. If you look back at the lecture video, they may go through an example of why that's not possible. So what can we reduce? The things that we can reduce are common factors. Factors can be reduced. So on top, 5 is a factor because nothing is being added or subtracted to it. You might say, well, aren't factors things that are multiplied? You could look at the top as being 5 times 1. So 5 is a factor. The denominator right now is not factored, but we can factor it. If we look at 15 and 75, 5 goes into both of those. But also 15 goes into both of those. If you don't recognize that, we could list the factorization, the prime factorization for 15. That's 3 times 5. 5 goes into 75. What's that? 15 times. 15 is 3 times 5. So if we're looking for what is the biggest common factor, what all do they have in common? They both have a 3, and they both have at least one 5. So our greatest common factor is 3 times 5, which is 15. So on bottom, if we pull a 15 out, 15, if we take a 15 out of 15x, we're left with an x. And 75 is 15 times 5. So if we pull the 15 out, we're left with a 5 there. Keep in mind, 15 is 3 times 5. Normally, I wouldn't break it apart that far, but just to illustrate a point. So my math lab is going to make this way harder than it has to be. We have this factored, and we can reduce it at this point. But the way my math lab shows you to do this, they throw in an extra step just to help you understand why it's factors that you can reduce and not other things. So they're going to say, well, the top, which is 5 times 1, we have a 5 on top and we have a 5 on bottom. So let's rewrite our fraction by pulling the 5s out front. On top, we're left with a 1. And if we take the 5 out front, we're left with a 3 and an x plus 5. Notice we still have 5 times 3, that's our 15, and we still have our x plus 5. So they illustrate this so that we can see, well, what is 5 over 5? 5 over 5 is 1. So if we have the same factor on top and bottom, when we pull that factor out front, anything divided by itself makes 1. 1 times anything is itself. So we're not going to have to show all those steps, but as long as we have a common factor that we could put out front, the same factor on top and on bottom cancel each other out, and that's going to leave us the remaining factors. But that only works with factors. It doesn't work with things that are added. Let's look at an example of that. Just a simple example. Let's look at 4 over 8. Now, a lot of you may recognize that 4 over 8 reduces to 1/2, or if you convert that to a decimal, is 0.5. But just for illustration, let's rewrite 4 as 2 plus 2 and 8 as 2 plus 6. What we could not do is we could not cancel that 2 and that 2 because those are things that are added. Those are terms. They're not factors at this point, they're terms. Likewise, we could not cancel that 2 with that 6 because that's a term. If we did that, we would be left with a 1 on top, a 3 on bottom. Well, 1/3 and 1/2 are not the same thing. So we can't cancel things from top to bottom if even one of those is being added or subtracted with something, if it's a term. We can only cancel things between top and bottom if they are factors. So let's take a look at this one. We can't just go in and say, well, I want to cancel that x with that x, and 6 goes into 54 9 times. We can't do that because the 54 is part of a term, or is a term. It's being subtracted from something. The x is part of a term. That is being subtracted from something. 9x is a term. So if it's a term or part of a term, we can't use it to reduce the fraction. It has to be factored. So the numerator has a common factor of 9. The first term is 9 times x. 54 is 9 times 6. So we took our common factor out front. On bottom, we have a common factor of x. So if we take one of the x's out, we're left with 1. For 6x, if we take an x out, we're left with a 6. So on top, we have two factors, 9 and x minus 6. On bottom, we have x and x minus 6. So since x minus 6 and x minus 6 are the same factor, we can cancel those. Again, we don't have to write this step, but we could break this apart and call this 9 over x times x minus 6 over x minus 6. Remember, when you multiply fractions, you multiply straight across. So this would be equal to 9 times that parenthesis, 9 times that, over x times that parenthesis, which is what we have. X minus 6 over x minus 6, that equals 1. Anything times 1 is itself. Again, I'm not going to make you show this step. I just did that to illustrate that if it's a factor, yes, we can cancel that out from top to bottom. Okay, here, we need to reduce this. So it's not factored right now, so we need to factor it. On top, both terms have at least x squared in them. So if we have x cubed and we take out x squared, we're left with one of those x's. If we have 11x squared and we take out an x squared, we're left with 11. On bottom, there's not a common factor between all three of those. But if we break it apart as the parentheses, x squared is x times x. That's negative, so we need a positive times negative. And then what numbers multiply to make 99 and have a difference of 2? Well, that would be 11 and 9. So we have a product on top, a product on bottom. Those factors are the same, so we can cancel those. So we have x to the second on top, x minus 9 on bottom. Now some of you are going to look and say x is a factor there because that's really x times x, and that is true. But we cannot cancel one of those x's with that x because this x is not a factor. It has something subtracted from it, so it's a term. So if the piece on top or the piece on bottom that we want to use is a term or part of a term, we can't use it to reduce. So x squared over x minus 9, that's what that reduces to. Okay, we look at this one. We can do this a couple of ways. Often we've mentioned before that we like to have the variable term first and then the number. So we could call this minus m squared plus 9. And if the leading term is negative, we like to factor out a negative. So remember what happens when we factor out a negative, it just changes each sign. So the minus m squared becomes positive m squared on the inside. Positive 9 becomes a minus 9 on the inside. If we check that, this minus would change that to a minus m squared, which is what we needed. That minus would change that to a positive 9. So we just pulled a negative out front. Inside that parenthesis, that's a difference of squares. That's a difference of squares. That's m that's being squared, and 9 is 3 squared. So we factor that as m minus 3, m plus 3. So the factoring we did in the previous chapter, that's important. We have to be able to do that in order to reduce these. Now on bottom, you might say, well, I don't have any factors. I just have things subtracted. And that is true to an extent. We do have things subtracted. But we could put a parenthesis around that. That doesn't change its value. But that whole thing is one factor. We could look at that as that times 1. So m minus 3 on bottom is a factor as a whole. So we have an m minus 3 on top, m minus 3 on bottom. Those cancel. So on top, we're left with a negative. We're left with an m plus 3, and on bottom, we're just left with a 1. And if the 1 is on bottom, we don't have to write it. Anything divided by 1 is itself. If I take anything and divide it by 1, it's itself. So I got a 1 on bottom, I don't have to write it. Now let's do this one another way, because this is going to come up from time to time. We could factor this directly. Instead of pulling a negative out and then factoring it, we could say, well, 9 is a square and this is a square. So we could just write that as it's 3 being squared and m being squared, and then put a plus in between them. And that's a factor. But if we first look at that, we don't have any factors that are exactly the same, but we do have factors that are opposite of each other. Those are exactly opposite. The m on top is negative, the m on bottom is positive. 3 on top is positive, the 3 on bottom is negative. So those factors are exactly opposite of each other. If we have things that are opposite, we'll look at a simple example. Those are opposite. 3 and negative 3 are opposite. When we cancel those, 3 over 3 is 1, positive over negative is negative. Negative 8 divided by positive 8. Those are opposites. 8 over 8 is 1. Negative over positive is negative. And that's going to be true no matter how complicated our factors are. If they're exactly opposite of each other, we can cancel those, but they don't make 1, they make negative 1. So we're left with a negative 1 times 3 plus m on top and just an understood 1 on bottom, or we could call that minus 3 plus m, or negative 3 plus m. I think on the other one we called it m plus 3, but m plus 3 and 3 plus m are the same. All right, let's take a look at this one. On top, both terms have a 7. 28 is 7 times 4. And both have an x squared. So if we take the 7 and the x squared out of the first term, we're just left with a 1. If we take the 7 and an x squared out of the second one, we're left with a 4 and an x. If we were to multiply that back together, that should check out. On bottom, 12 is 3 times 4, so both terms have a 3 and both terms have an x. So if we take a 3x out of there, we just have a 1 left. The next one, if we take a 3 out and one of those x's out, we're left with a 4 and an x. So once we have it factored, notice the parentheses match. The parentheses are factors, so all of that divided by all of that makes 1, so that cancels. We can cancel some more. The x's here are factors. We don't have to do this, but x squared means x times x. So these x's are factors. All of this is multiplied together, not added or subtracted, so factors. X is a factor because it is something's multiplied with it, not added. So if we have the same factor on top and bottom, those cancel. So we're left with a 7 and an x on top, and we're left with a 3 on bottom. So we've canceled out the common factors. Again, feel free to do the step that my math lab shows where we pull out the common factors to the front so that we can see anything divided by itself makes 1, and that's what we're left with. But if you recognize they're factors, you can just cancel them out there and write what you're left with.